Hello everyone, welcome to the channel Statistica. So in previous lecture we have covered the concept of inverses of matrices. Now we'll see the rank of a matrix. Okay, so for rank, let's look at in the linear transformation way. That in the linear transformations we have studied this. That rank is basically the maximum number of linearly independent rows as well as columns in a matrix. Okay, so what is the rank? Rank is number of linearly independent rows as well as columns in any matrix A. Let's just consider the matrix A. Okay, and the matrix A is of order m cross n. Okay, and if we look to the denotation of the notation of this rank, then the rank of this matrix A is actually denoted as rank of A. This is how we can denote the rank, which is said as rank of matrix A. Now, here is the matrix A, and let's just consider that the rank of this matrix A is actually equals to R. Okay, so what does this mean? It means that maximum number of linearly independent rows as well as columns in A is R. Okay, and other thing is that there are m minus r linearly independent relations between rows of A, and you can also say it like this, that there are n minus r linearly independent relations between columns of A. Okay, so these are actually the linearly independent rows and columns. And as you can see that if we are considering a matrix of A of m rows and n columns, so from this we got that if we have a rank of R, then there are m minus r linearly independent relations between rows of A and n minus r linearly independent relations between columns of A. Okay, so for finding the rank of a matrix, we can use the concept of minors in the determinant. Okay, so if we have a matrix A, which is like, let's just consider this matrix like 1 1 2 1 1 1. Okay, 2 1 1, 1 1 1 minus 1 1 2. Okay, so this is my matrix. So this is my a11, a12, a13, similarly a21, a22, a23. Okay, so if we want to find the minor of an element, okay, the minor of an element, then the minor of an element in a matrix is defined as the determinant obtained by deleting the row and columns in which the element lies. What is the minor? The minor of an element in a matrix is defined as the determinant obtained by deleting the row and column in which that element element lies. Okay, so if I want to find the minor of this a11 element, that is for 2, then what is this? We have to delete the row and the column corresponding to this matrix corresponding to this element. Okay, so the minor for this a11 is the determinant of the remaining elements, that is 1 minus 1 1 2. Okay, this is the minor for a11. And similarly, if you want to find the minor for a12, what is the minor for a12? Minor for a12 will be, we'll cut this row and this is my a12, we'll cut this row and this column, and the remaining will be 1 1 1 2. Okay, it is determinant of 1 1 1 2. Okay, and similarly minor of a13. What is minor of a13? Minor of a13, we'll have to delete this row and this column, and we'll got this, that 1 1 1 minus 1. Okay, so these are my minors for a11, a12, a13. So the determinant of these minors are, we can find the determinant as 1 into 2, 1 into 2, that is 2, minus minus 1 into 1, minus 1 into 1 is minus of 1, and that is equals to 3. Similarly, the minor of this is equals to 2 minus 1, 2 into 1 minus 1 into 1, and that will be equals to 1. And similarly for this, we got the minor as minus 1. Okay, okay, minus 1, and that is equals to minus 2. Okay, so okay, so this is how we can find the minor of an element for A11, A12, A13. Similarly, if we want to find the minor of the A21, A22, A23, or any of the element, then we can find the minor by deleting the row and column in which that element lies. Okay, and by taking the other element and taking the determinant of the remaining elements, we can find the minor. Okay, so if I want to find the determinant of this whole matrix, okay, then what do I have to do? That if we have to find the determinant of A, okay, then for that we have to multiply the element. Okay, that just like a11. Okay, so I am finding the minor for a11, and if you want to find the minor the determinant for this, so we have to take it 2. We are finding the minor for 2, so let write it like this 2. Okay, into minor of this 2. Okay, a11 into minor of this 2, which is 3. And similarly minus, we'll apply minus, plus minus plus, this is how it goes, and this is 1. So minor element, and into the minor of a12, that is 1, plus 1 minor element a13, and the minor of this a13, that is minus 2. And the determinant of this matrix is 3 to the 6 minus 1 minus 2, so we got 3. Okay, so the determinant of this matrix is 3. Okay, so we are just looking the basic of the determinant topic here. Okay, for finding the rank actually. Okay, so now just look to the definition of the rank, that how can we find it, that the number r is said to be the rank of matrix A. The rank of matrix A if conditions are, if every minor of A of order r plus 1 is 0. Okay, so in the first condition we have said that rank r, the number r is said to be the rank of this matrix A if every minor of A of order r plus 1 is 0. Okay, and the second condition is that the matrix A possesses at least one minor of order r which does not vanish. That means the matrix A has at least one minor of order r which does not vanish, which doesn't have a determinant as 0. Okay, and you can also define the matrix like this, the rank of the matrix like this, that the every square submatrix, if every square submatrix of A of order r plus 1 is singular. That means if we have a matrix of if we have a rank r, then the matrices of order r are non-singular, and the matrices of order r plus 1 are singular. Okay, and the second condition is that there is at least one square submatrix of order R which is non-singular, which is non-singular. Okay, so if we are talking about the rank, then in the second condition we have said that there is at least one square sum matrix of order R which is non-singular. Okay, so if we are saying that A is my matrix, and if a matrix contains at least one non-zero element, okay, there is a one non-zero element in a matrix, then it means that the rank of matrix A is greater than equals to 1. Okay, if the matrix contain at least one non-zero element, I'm not saying about the, I didn't know anything about the order of this matrix, but I am just giving the statement that if a matrix contains at least one non-zero element, then the rank of this matrix A is has to be greater than equals to 1. Okay, now if we look into the matrix identity. Okay, if I have the identity matrix which is as 1 0 0 0 1 0 0 0 1, you can clearly see that uh, by the definition that the rank of this matrix, identity matrix of 3 cross 3 is 3. Okay, so if you look to the definition of minor, that the every minor of A of order R plus 1 is 0. If you look to the determinant, that the determinant of this identity matrix is actually 1. Okay, so by the determinant definition that it is a non-singular, the determinant of this identity matrix is non-singular. Non-singular. So from this you can say that the identity matrix is of rank 3. Okay, and the rank of a zero matrix. If we have a zero matrix, then the rank of the zero matrix is taken as 0. This is the only matrix which has 0 rank. Otherwise, there exists some element in matrix that should have a rank greater than equals to 1. Okay. Okay. Now let's just see them by the examples. That if we have a matrix A of m cross n, then it means that this is the property actually, that it means that the rank of this matrix A has to be less than equals to minimum of m comma n, that is minimum of number of columns and number of rows. Okay, this is the property that we have, that if I have a matrix A of m cross n, then the rank of A is basically the uh, minimum of m comma n. Okay, so let's just consider the matrix A like 1 3 minus 2 minus 6 minus 1 minus 3 0 1. Okay, this is my matrix A. So by this property we have this is the matrix of 2 cross 4. There are 2 rows and 4 columns, so the rank of A has to be minimum of 2 comma 4. So we got that the rank of A is less than equals to 2. Okay, so if we look to the from the minor concept, that there are 2 cross 2 4 minor matrices. There are 2 cross 2 minor matrices in this matrix. Like the minor matrices are like 1 3 minus 2 minus 6. Okay, we have to take out the minor matrices here, which are and minus 2 minus 6 minus 1 minus 3. This is my second minor, and there are 1 3 0 1. This is my third minor, and minus 1 minus 3 0 1. Okay, so if every minor of A of order R plus 1 is 0, then we have said that then the number R is my rank. Okay, now let's just find the minor of these elements. Then what did we get? We got minus 6 plus 6, that is equals to 0. And the minor of this matrix is 6 minus 6, that is equals to 0. And for this we have 1 minus 0, that is equals to 1. Okay, which is not equals to 0. And for this we have minus 1 minus 0, and that is equals to minus 1, and that is also not equals to 0. Okay, so from this we can see that there are two minors here. There are two minors here which doesn't vanish, which does not vanish, and it is satisfying the condition that the minor here, that there are at least one minor of order R which does not vanish. So these are the minors of 2 cross 2, minors of 2 cross 2, and we possess two minors here that does not vanish. So the rank of this matrix by the minor method is 2. Okay, so by the for the minor method you have to take out the minor and solve the determinant for that. Okay, and you can apply this for checking the condition here like this, and you can find the rank by the elementary transformation methods, and that is I think easier because you have to just apply the transformations and you got the corresponding echelon form in that case. And you can easily see that there are how many number of linearly independent rows, linearly independent columns in that, and find the rank of the matrix. Okay, so let's just find the rank of a matrix by the use of elementary transformation. Rank of matrix by elementary transformation. Okay, so this is the method that we mostly use for finding the rank of any matrix. Let's just see that my matrix is as 1 2 3 2 3 5 and 3 4 7. Okay, this is my matrix and I have to reduce it to the echelon form. Okay, we have done this so many times that if I want to reduce this matrix to the echelon form, so let's just apply the transformations which are as in R2 we'll apply R2 minus 2 R1. For R3, in the R3 we'll apply R3 minus 3 R1. Okay, and from this we got 1 2 3, and this is my 2 minus 2 0, 3 minus 4 minus 1 minus 2, and similarly 3 minus 3 0, 5 minus 6, that is minus 1 and minus 2. Okay, now we'll apply this here, then we'll do R3 minus R2, and from this, by this transformation we got 1 2 3 0 minus 1 minus 2 0 0 0. Okay, so this we I got my corresponding echelon matrix here. Okay, because it can't be reduced further. So the elements that I got, these are my corresponding elements here. Okay, so here I got the number of non-zero rows. I have to check the number of non-zero rows. The number of non-zero rows here are 2. Okay, I can clearly see that I have two non-zero rows. So from this we got that rank of A is equals to 2 here. Okay, let's just look same example for this. That's if I have a matrix of 0 1 3 1 2 1 2 3 1 1 2 3. Okay, now this is a matrix of 3 cross 4. Okay, this is a matrix of 3 cross 4. Now if we want to apply the use solve this matrix by the elementary transformation method, then we can do it like this, that let's just interchange these rows which is r1 to r2. So this will be 1 2 3 2 0 1 2 1 3 1 1 3. Okay, and let's just apply the another transformation which is on r3, r3 minus 3 r1, and that would give us 1 2 3 2 0 1 2 1 0 minus 5 minus 8, and that would be 3 3 3. Okay, that would be minus 3. Okay, now let's apply another transformation which is on r3. Okay, so this would be r3 plus 5 r2. Okay, and this would give us 1 0 0 2 3 2 1 2 1, and that will be 0 2 2. Okay, so here we got that the number of non-zero rows here are 3. Okay, so from this we can see that the rank of this matrix, let's just say this is the matrix A, so rank of this matrix is equals to 3 as there are 3 non-zero rows here. Okay, so this is how we can find the matrix, that the rank of the matrices by the minor method and by using the elementary transformation. Okay, now there are some properties of the ranks, like first we have studied this, that the if we have a matrix A of m cross n, then the rank of A is less than equals to minimum of m cross n, m comma m. Okay, minimum of number of rows and number of columns. Okay, and second property is that if we have determinant of A is not equals to 0, that means the matrix is non-singular. The whole matrix is non-singular, so no minors is 0. No minors is 0. Okay. So if we have the matrix A which is non-singular, then we have no minors which are 0. And the third property is that the rank of A is equals to rank of A's transpose. Okay. So the transpose of a matrix has the same rank as the matrix A. And the fourth property is, we have also done this. Let's just write it down here, that the rank of a zero matrix is 0. Rank of a zero matrix is 0. Okay. And the fifth property is like this, that the rank of sum of two matrices A plus B. If we have two matrices A and B, then the sum of these two matrices rank is actually the less than equals to rank of A plus rank of B. Okay, this is the corresponding property, and we have finded this property by using the uh, inequality, which is mod of A plus B is less than equals to mod of A plus mod of B. This is the inequality we have studied earlier. Okay, so by using this property we have gained that the sum of these two matrices, rank of A plus B, is less than equals to rank of A plus rank of B. Okay, now let's just see it like here, that if I have two matrices, that A which is of 3 cross 3, and I have another matrix which is B which is also of 3 cross 3. Okay, and we have taken the multiplication of these two matrices A B, and I want to find the rank of this. The rank of this matrix A B. Okay, so for the multiplication of these two matrices, rank of AB, we have the property as that rank of AB is basically less than equals to minimum of rank of A comma rank of B. Okay, now this is the very important property, and this is said to be the upper bound of rank of AB. Okay, this is the upper bound of the rank of AB. So if we have matrix multiplication of A, B, and if we want to find the rank of these matrices, so the rank of A, B is less than equals to minimum of rank of A, comma rank of B. Okay, so we have rank of A, B here, which are of 3 cross 3, and B is of also 3 cross 3. And let's just say the rank of this AB is equals to 1. We have given this. Okay, so rank of BA, rank of BA can't be, I'm giving you options which are as let's say, can't be 0, can't be 1, can't be 2, can't be 3. What is the right option? So we have given that the rank of AB is equals to 1. Okay, so if you look this closely, so if we have rank of AB is equals to 1, that means it is singular here. It is singular, that means determinant of AB is equals to 0. As its rank is 1, by this property, if determinant of A is not equals to 0, then it is non-singular. But we have rank of AB is equals to 1 here. So determinant of AB is equals to 0. Okay. And we can write it down as determinant of A, determinant of B is equals to 0. That means that determinant of A is equals to 0, or determinant of B is equals to 0. Or for checking the condition for BA, so for the determinant of BA, we can write it as determinant of B into determinant of A. So from this we got that either the determinant of B is 0, either the determinant of A is 0, by using this. Okay, so the rank of the matrix BA can be 0, can be 1, can be 2, but it can't be 3. It can't be 3, because we have the by this property here, we have determinant of A is equals to 0 and determinant of B is equals to 0. So if we have a 3 cross 3 matrix, A of 3 cross 3, and if its determinant is not equals to 0, so the rank of this matrix can't be 3. The rank of this matrix can't be 3, because here there exist minors which have value as 0. And by this property, in this we have seen this, that if we have determinant of A is not equals to 0, then there are no minors which have value 0. Okay, So by this property we can see this, that we have determinant of A is equals to 0 and A is of 3 cross 3. So we can't have the rank of this matrix A and B as 3. Okay. Okay. So what is my next property, which is sixth property is that the rank of AB is less than equals to minimum of rank of A comma rank of B. Okay. Now if A is non-singular, let's just consider, then one of them AB into in the matrix multiplication of AB, we have A matrix which is non-singular, then the rank of AB is equals to rank of B. Okay. And if B is non-singular, then rank of AB is equals to rank of A. Okay. So these are basically the property that rank of AB is equals to rank of B and rank of AB is equals to rank of B, because uh, in this case we say that the column space of AB, if we look to the column space concept, that the column space of AB is equals to column space of A. Okay. And it means that the column space of AB is equals to the column space of A. Okay. So this is what we have done in the column space also. Okay, that the column space of a matrix AB are basically the number of linearly independent rows, not linearly independent columns actually. Okay, the number of linearly independent columns. Okay, and here rank is also that the maximum number of linearly columns in a matrix A. Okay, so I can write it down like this also. Okay, so this is the my upper bound here, upper bound for rank of AB. And if we look to the lower bound of rank of AB, then what will be the lower bound of the matrix? The lower bound of the matrix AB is the rank of AB is actually by the Sylvester's inequality. Sylvester's inequality. So by the Sylvester's inequality, the rank of AB is greater than equals to rank of A plus rank of B minus N. Okay. So this is the lower bound for rank of AB by the Sylvester's inequality. So in the next lecture, we'll look at these two things, that is upper bound and lower bound of the matrices in the more deeper concept, that how these are actually gained, that how we got the rank of AB as minimum of rank of A and rank of B, and how we got the lower bound of the matrix of rank of AB. And there are some important concepts in the rank too, that is rank factorization theorem and ranks on the basis of real and complex matrices, because we are more interested in the fields of real and complex. Okay, so we'll just take a special case here of real and complex. So let's meet in the another lecture of the rank concept. Thank you.